Hi, and welcome back to Maskey TV. Here at Maskey Miller Learning, we are so thrilled to have you for the topic of Euclidean geometry, one of my favorite topics in mathematics. Our lesson objectives for today will be to run through some of the Euclidean geometry theorems, as well as looking at the proofs, and we are going to go through the Dr. Cape Town approach, as well as talk about some acceptable reasons, and thereafter we will go through an exam type question. Are you ready? Let's go. All right, first of all, we are going to talk about the parts of a circle. The parts of a circle, we have over here a circle, we have our center. If we have a line that goes from a point on the circumference to another point on the circumference, we call that a chord. A chord that goes through the center is called a diameter. Chords divide circles up into segments. So this shaded area over here we call the minor segment, and this area over there will be the major segment. We also have from the center to the circumference, we will call that the radius. If we have two radii, we will have what I like to call a pizza slice. A pizza slice is a sector. Another thing that's very important is an arc length. So an arc length is if we have 2 points on the circumference. So let's say that is point A and this is point B. This length over here is called an arc. And a tangent. A tangent is a line that touches the circle at one point only. So let's call that point C. It's touching the circle at point C. Now we're going to look at some theorems. I've just grouped the theorems together just to put them back on the screen and so that you can have a look at them again. Remind yourself of all those 9 theorems and converses. Not all of them have converses. However, we do need to remember when to use which theorem. So what I've done is I've just grouped together the ones that require or have a center or a diameter or a radius. And so, for example, we have this one over here. This one is line from the center, which is center O, to a chord AB. It's a perpendicular line from center to chord. So all of these theorems over here, these ones either require a center, a radius, and what do we think of when we have radii? We think of isosceles triangle, and it also has a diameter. We think of angles in a semicircle. So those are the ones that require a center, a radius, or a diameter. The ones on the board over here, these require 4 points on a circle, which is a cyclic quadrilateral. We use the term concyclic. Concyclic means lies on the circumference, on the same circle. Concyclic. Concyclic. So for example, E, D, G, F, they are concyclic points. And for a cyclic quadrilateral, we have to have 4 points on the circle. So all of those are theorems involving cyclic quads. For example, exterior angle of a cyclic quad is equal to the opposite interior angle. And we have some over here. This one over here is your angles in same segment. Not really classified as a cyclic quad. However, I've put it in, I've grouped it here. Why? Because we need to have 4 points on a circle. I just want to go through this one a little bit more. So if we have a circle, and we have 4 points on a circle, A, B, C, D. All right. I like to call this theorem the bow tie theorem or the butterfly theorem. It's a nice way to remind us of angles in the same segment. The angles in the same segment are A and B. They are then equal to each other. And if we turn it around, then D and C will also be equal to each other. And then lastly, we have our tangent theorem. So in order to use these theorems, it has to have a tangent. For example, we have tan-chord. The angle between the tangent and the chord BE is equal to the angle in the alternate segment, which is angle D over there. So those are all of your theorems that you need to know. Let's have a look at proving cyclic quad. So there are 3 ways to prove something is, 4 points lie on a circle, which is a cyclic quad, and that is this one over here. This is a converse of angles in same segment. This one over here is converse opposite angles of a cyclic quad, and lastly converse exterior angle of a cyclic quad. So it's the 2 cyclic quad theorems, but the converses, and the angles in same segment, but the converse. This is what we use to prove something is a cyclic quad. All right, we're going to get stuck into a question. So let's read through it together. ABED is a cyclic quadrilateral. FDCG is a tangent to the circle at D. BEC is a straight line. They also give us parallel lines AD parallel to BC, and they tell us that AD is equal to AE. And then they also tell us that ADE, angle ADE, is equal to X. Let's highlight where ADE is on our diagram. So ADE is equal to X, that's over here. Right, let's go through what I like to call the Dr. Cape Town approach. So we have D, R, C, P, T. Now these letters represent something on that diagram. It's going to help us, remind us of our theorems. It is many of the most important theorems to remember. And it is not all of them, but it does really help us when analyzing a diagram. Always think of Dr. Cape Town. So what does the D represent? The D represents the diameter. The R represents the radius. The C represents cyclic quads. Do we have a cyclic quad? The P represents parallel lines. And the T represents tangents. Now, before I go any further, I'm going to look at Dr. Cape Town with regards to this question, but I just want to quickly stop at parallel lines. So when we think of parallel lines, what do we think of? We think of fun angles, F, U, and N. Those are your corresponding, your co-interior, and your alternate angles. Right, so that is your fun angles. Let's look at our diagram again. So what we're going to do now is we're going to use Dr. Cape Town to help us analyze this diagram. So we have D over here. What we're going to do is we're going to check, do we have a diameter? And if we look at the diagram and the information, we do not have a diameter. So we're going to say, nope, no diameter. R for radius. Do we have a radius? No, we don't have a radius here. Do we have a cyclic quad? Yes, we do. ADEB is a cyclic quad. So now we're thinking of those cyclic quad theorems that we can use. Our exterior angle of a cyclic quad and opposite angles of a cyclic quad. This should come back to us. Parallel lines. Yes, we do. We have AD parallel to BC. Right, so we've got maybe, possibly some fun angles happening there. We must think of our parallel lines. So we do have parallel lines, we do have cyclic quads. And lastly, do we have a tangent? Yes, we do. FDCG is a tangent to the circle. So we do have a tangent, and we have those tangent theorems that we need to think of. What I would like you guys to do is, I'd like you to take your pen and paper and go through these questions. Now that we've analyzed it, we know what's happening in the diagram. I'd like to see if you can work out the 5 other angles equal to X. And don't forget to add your reasons. Thank you. We'll be back in a bit. Welcome back. Let's go through the questions. So it asks us to find 5 other angles equal to x. So remember, we've analyzed it. We have a cyclic quad over here. We have parallel lines. We also actually have 2 pairs of, or rather 2 sides that are equal. They also told us that AD is equal to AE. And that we must think of an isosceles triangle. And that I think is the first one that is jumping out at me. And I'm going to have a look at that one. So I've got an isosceles triangle over here. AD equals AE, which would make the base angles, which is D over here, x, equal to E2. So this angle over there is also equal to x. So we're going to say E2 is equal to x. And the reason that we use is we cannot use isosceles triangle. We have to use angles opposite equal sides. And remember, we also have to write out the word equal. We cannot use the equal symbol for that one. All right, then the next one I'm looking at, let's see, what do we have here? We have the cyclic quad. I am seeing a fun angle. Let's highlight it. So I've got my parallel line there and my parallel line there, and I'm seeing the Z over here, which is telling me that if that is x, then E3 is also x because of alternate angles. So E3 is also x, and our reason is alternate angles. Don't forget, whenever we use one of the fun angles, we have to give the pair of parallel lines, and that is AD parallel to, I'm going to use the whole line, BC. Right, let's see what is next. I mentioned the cyclic quad, and I'm seeing this angle over here, which is the exterior angle of the cyclic quad. I'm just going to highlight it there. Exterior angle of the cyclic quad. So that means it is equal to the opposite interior angle, which is this angle over there. So how do we write that angle? We say BAD, bad. Angle BAD is equal to x as well. And what is our reason? It is going to be exterior angle of cyclic quad. All right, let's label that angle x over there. Okay, let's see, can we see any more? I'm seeing the tangent. Why is the tangent there? Remember, Dr. Cape Town, we had our cyclic quads, we had our tangent, we had our parallel lines. What can we think of with regards to our tangent? I see this angle over here. I see D1 over there. Let's see what's happening. This angle, D1, is the angle between the tangent FC and the chord AD. AD subtends E2, which means that D1 must also be equal to x. Reason is tan-chord theorem. So we've got D1 equal to x, and my reason is tan-chord theorem. Right, we've got 1, 2, 3, 4. We just need one more, and let's go. I think I need to highlight it so you can also see. We've got these, I'm going to rewrite parallel lines. So I've got this parallel line, I've got that parallel line, I've got my transversal over here, which means that this is an F. Can you guys see the F shape? FD1 and C1. C1 is also equal to x because of corresponding angles. So we've got C1 equal to x. The reason is corresponding angles. And remember, whenever we use one of the fun angles, we have to give the pair of parallel lines. AD parallel to BC. All right, we found the 5 angles equal to x. Let's move along. And I want to go through with you something that I feel every grade 11 should know about. It is the examination guidelines. This can be found on the DBE website. The latest one is the 2021 grade 12 guidelines. Yes, it is grade 12. However, if you read through the guidelines, it gives you all the reasons, acceptable reasons for geometry. It gives you reasons from grade 8 geometry up until grade 11 geometry. In fact, it does go a bit further to grade 12 geometry as well. It gives us all the acceptable reasons for your circle geometry. So for example, let's just look at the first one. I'm not going to go through all of them, but the tangent to a circle is perpendicular to the radius or diameter of the circle at the point of contact. That is our theorem, right? That is our tan perpendicular to radius theorem. But we're not going to write that whole sentence down. We're going to use a reason in brackets after our statement, and the acceptable reason is tan perpendicular to radius or tan perpendicular to diameter. And those are the only acceptable reasons. So if you use other reasons, you might get marked down. So it's very important for you to have a read through and make sure you know your acceptable reasons. All right, we're going to go through another question. Question 9, this comes from the DBE website. It is 2019, paper 2. Euclidean geometry is in your paper 2. And let's go through it. So it says, in the figure, Q, P, T, S, and R lie on the circle. M lies on QS such that PM is parallel to SR and PTS is equal to 145 degrees. Okay, let's go back to Dr. Cape Town. So let's see if we have anything happening there. I'm going to leave the fine angles there because that helps us. Okay, D for diameter. Do we have a diameter? No, we do not. They have not given us a diameter in this question. Do we have a radius? Unfortunately, we do not have a radius because we do not have a center. Do we have a cyclic quad? I'm actually seeing two cyclic quads. We see P over here, P, Q, S, and T. And then I see another cyclic quad, which is P, R, S, T. So I've got two cyclic quads over there. Then they ask, do we have parallel lines? Yes, we do have parallel lines. Do we have a tangent? No, we don't. I think, grade 11s, I think you should go through this. We'll give you a few minutes, and then we'll go through the answers together. Welcome back. I hope you took your pen and paper and you were going through this question. Remember, we have a cyclic quad, not one, but two, and we have a pair of parallel lines over there to look at. So let's start answering the question. Let's go. Calculate the size of Q. Q is the angle. I'm just going to highlight Q. Q is the angle over here. And as we can see, if we remember our Dr. Cape Town, it told us that we had the cyclic quad PQST. We had to analyze it, and we can see that T, which was the given angle, 145 degrees, is in fact opposite to angle Q. So that would mean that Q is equal to 180 45. So Q is equal to 180 degrees minus 145 degrees. Right, our reason is opposite angles of a cyclic quad. And Q equals 180 degrees minus 145. That gives me 35 degrees. Let's go to the next one. We are looking for R. R, where is R? Let's highlight where R is. R is over here. And remember what I said earlier on about the butterfly? I'm seeing my butterfly. Let me highlight it for you. Let me highlight it for you. So can you see the butterfly? All right. If we have this happening, we've got 4 points on our circle, it would mean that this arc PS subtends angle Q and PS also subtends angle R, which means that those angles are in the same segment and they will be equal to each other. So that means that Q is in fact equal to R, which is equal to 35 degrees. Your reason is angles in same segment. Okay, let's go to the next one. Angles in same segment. The next one is P2. I think I'm going to fill in on my diagram. It's always good to fill in on your diagram. So we've got 35, as highlighter is still on, let me put it on, 35 degrees over there, 35 degrees over there. We are now looking for P2. P2 is this angle over there. And if we look at P2 is also about 2 marks. I'm seeing the parallel lines over there. So I've got PM. Let me highlight those parallel lines quickly. PM is parallel to SR. And that means we have alternate angles over there. P2 is also equal to 35 degrees. Let me put it on the other side. P2 is equal to 35 degrees. Let's write our reason. P2 equals 35 degrees. Our reason is, oh, that looks like a 38. 35 degrees. Our reason is alternate angles, right? We said we had parallel lines. Alternate angles, and we mustn't forget to list the parallel lines. PM is parallel to SR. Okay, let's have a look at the last question. It says that Y is PR a tangent to the circle passing through PMQ. So there isn't a circle at the moment passing through PMQ, so I'm going to try my best to draw a circle passing through PMQ, because the best way to answer a question where they ask you to show that or prove that there is a tangent passing through a circle where there isn't a circle, draw the circle. It will help you understand how to answer that question. So PMQ, let's try my best to draw a nice neat circle through PMQ. Okay, not as neat as I would like it, but I think we get the idea. So what we need to do, and I can see already, to prove something is a tangent, I have 2 converse tangent theorems, and that's your tan-chord, the converse of tan-chord, as well as tan perpendicular to your radius. But I do not have a center for this circle, so I'm looking at tan-chord. Let me just get rid of some stuff here. Let's erase quickly everything, and let's just quickly look at that a little bit better. Maybe my circle will come out a bit better. Remember that P2 was, in fact, 35. Q was 35. R was 35. Okay, so what we can see here is we're trying to prove that PR is a tangent. So PR, let's highlight PR. This is PR. So if PR is a tangent, that would mean if we're using converse tan-chord, then this angle must be equal to that one over there. And we do have that happening. And so because we have that happening, we can then conclude that it is a tangent to that circle PMQ. So we just have to state that P2 is equal to angle Q, which is equal to 35. It was given, we've proven it already. You can say proven above. And therefore, PR is a tangent. But now here comes the important part. It is the reason we are going to give for why it is a tangent. And the reason we're going to give is converse tan-chord theorem. All right, that was lovely. We did a lovely exam type question from the DBE paper. Let's go to the next one. All right, question 10. So this question, in the diagram below, O is the center of the circle, PTS are points on the circumference of the circle, PS, PT, and OT are drawn. This question asks, prove the theorem which states that SOT, let's just highlight SOT, SOT, that is this angle over here, right? SOT is equal to 2 times SPT. SPT, it's that angle over there. All right, so this question we would say is a formal proof. Remember, this is very different to proving something is a tangent, proving something is a cyclic quad. In this question, we are in fact proving a theorem. And there are 5 theorems that you need to know the proofs are, and this is one of them. Let's go through it together. The very first thing we're going to do is we're going to construct something. And for each theorem, we do a construction. So our construction for this one, because we need to prove that SOT is equal to double SPT, the construction we're going to do is we're going to draw a line through PO. Okay. So what I like to do is I like to write down what I'm required to prove, RTP, required to prove. They're asking us to prove that SOT is equal to 2 times SPT. So that's what I'm required to prove. The next thing I do is I tell my examiner what construction I am making. Okay, I'm joining the line PO. I'm making a line PO. Right, that's the construction I have made. Now for this proof, the very first thing I would do is I would write on my diagram. Remember, they give you the diagram. You make the construction. I'm going to write a 1 and a 2. That represents P1 and P2, O1 and O2. Okay, the next thing I do is, this is on my paper, that's my diagram sheet. I'm going to talk to that diagram. So the first thing you're going to do is you're going to say that O1 is in fact equal to P1 plus angle S. And the reason for that is exterior angle of a triangle. So O1 is equal to P1 plus angle S, and that is your exterior angle of a triangle. Okay. PO, we're going to join, sorry about that, join PO. Right. Then, the next thing that we are going to do is we are going to state that PO and OS are in fact radii. They are radii. They come from the center to the circumference. So we're going to say PO is equal to OS, and my reason is they are radii. Now, if they are radii, that would mean that angle P1 is equal to angle S. Angle P1 is equal to angle S. And the reason for that is angles opposite equal sides. Okie dokie. Now the next thing we need to do is, because P1 is equal to angle S, we can restate this as O1 is equal to P1 plus P1, which is in fact 2 times P1. So O1 is equal to 2 times P1. All right, we're almost there. O1 is equal to 2 times P1. Now, I'm not going to do it, but for the other side, if we do the same method for O2, we can prove that O2 is also equal to 2 times P2 by doing the exact same thing we did for O1. So all we do is we say similarly, if we do the same on the other side, we can prove that O2 is equal to 2 times P2. Right, so if we do the same thing for the other side, we can prove that O2 is equal to 2 times P2. All right, remember, what did they want us to prove? They wanted us to prove that SOT is 2 times SPT. What is SOT? SOT is simply O1 plus O2. So what is O1 plus O2? Well, if O1 is equal to, let me see if the highlight is going to work. If O1 is equal to 2P1, and O2 is equal to 2P2, then O1 plus O2 is equal to 2P1 plus 2p2. If I factor 2 out over there, I have 2p1 plus p2. All right, but remember, O1 plus O2 is actually SOT. And P1 plus P2 is actually SPT. So let's replace that. SOT is equal to 2. P1 plus P2 is SPT. 2 times SPT. And that is exactly what we were asked to prove right in the beginning, required to prove that SOT is equal to 2 times SPT. And that is one of the proofs that we need to know. And remember, we didn't use the proof of this theorem. What theorem is this? How do I know what theorem this is? Angle at center equals 2 times angle at the circumference. The angle at the center is SOT. The angle at the circumference is SPT. I am not allowed to use that theorem to prove that theorem. I have to use other axioms and theorems. All right, grade 11s, let's move on. So just so we are aware, I've put on screen the other theorems that you need to know. All 5, in fact, are on the screen. You can pause if you want to read through them all. So there are 5 proofs that you can be examined on, and those are the 5 proofs there. The one that we did was the angle subtended. No, it was angle at the center. Where is that one? Angle at the center is equal to 2 times angle at the circumference. All right, okay, so let us move on. We are looking at an exam type question from the 2019 paper, paper 2. Moving on. In the diagram, O is the center. The points A, B, and C and D lie on the circumference of the circle. BOD is a diameter. AC and BD intersect at E. A1 equals 51 and B is equal to 29. Okay, remember we're going to go back to Dr. Cape Town quickly to help us analyze our diagram that we have over here, and then we will go through it together. Right, the first thing is, do we have a diameter? And yes, we do. They told us that BOD is the diameter, BOD. And so I'm going to tick diameter. Remember, we think of angles in a semicircle and all of those theorems that involve diameter and radii. Radius, we have a center, which means we do have a radius. In fact, we have a couple of radii over here. We have OD, OC, and OB. I'll just actually already indicate it on there. And then the next thing we are looking at is our cyclic quads. We do also have 4 points that lie on the circle. We don't have a closed line over here, so we won't be able to use opposite angles of a cyclic quad, but we can use that bow tie theorem, right? Which is in fact angles in a semicircle. All right, then the next one is parallel lines. Do we have parallel lines? Not in this question, so no. We won't be able to use any fun angles. We cannot use fun angles without parallel lines. And a tangent, do we have a tangent? Not in this question over here. So we're looking at our diameter and our questions that involve our center and radii. Okay, let's go through the first one together. Determine the size of O1. Let's look for O1. Let's look for O1. O1 over there, we have O1. We are asked to find O1. Let's highlight it. Right, I remember that I have my center O, and remember we just went through the proof of angle at center equals 2 times angle at the circumference. So if this is the angle at the circumference subtended by CB, right? And O1 is also subtended by CB at the center, it means this one is double the one at the circumference. So that would make O1 equal to 2 times A1, which is O1 is equal to 2 times 51, that's 102 degrees. And your reason is angle at center equals 2 times angle at circumference. Determine the size of A2. Where is A2? A2 over there. Let me just fill in what I found already. So this is 102 degrees. I'm making my drawings there. Okay, determine the size of A2. A2 is the angle over here. And we are now looking, how can we go about that? We have our radii, we have our angles in a semicircle. Let's see, how do we go about that one? Okay, I think I said it and then I saw it on the board. So angles in a semicircle, everybody. Let's look over there. Where is that angle? So A2. Whoop. There we go. So A2 is in fact part of this right angle over here. So can you see this is your diameter? And this dB subtends angle A, which would make that angle a 90-degree angle. And if this whole angle is a 90-degree angle, then A2 must be 90 minus 51. So A2 is equal to 90 minus 51, which gives us 39 degrees. 39 degrees. Our reason is going to be angles in a semicircle. Angles in a semicircle. Right. Okay, next one. D, we are looking for the whole of D. So this is this angle over here. Angle D. Let's just fill in what we know. A2 we said is 39. And D is only one mark. So, you know, looking at it, only one mark. We've got this triangle over here. We've got 39, 51, 29. We are going to use interior angles of a triangle, the sum of the interior angles of a triangle. So D is going to equal to 180 minus 39 minus 51 and minus 29, which is going to give us 61 degrees. So D is equal to 61. We use the sum of the interior angles of a triangle, right? That is 180 degrees, right? Minus, let's just bring this a little bit further over here. D, 180 degrees minus, let's say that is 90 and that's 29. So minus 90 plus 29, right? That will give us our answer of 61. 61 degrees. Let us put that on our board. So that is 61 degrees over there. Next one is determine the size of ACO. Where is ACO? ACO. That's this angle over here, right? Okay, so let's see. What can we do with ACO? It looks to me like we have to first find C2. Because if we can find C2, and we know that the bow tie theorem, or angles in the same segment, we know that this angle should be equal to that whole angle. Can you guys see the butterfly? Angles in the same segment. Okay, so how do we find C2? Well, C2, because we know that OC equals OB, which is radii, C2 will equal to 180 degrees minus 102 divided by 2, because these two angles will be equal to each other. B2 and C2 will be equal to each other. Okay, so the value of C2, 180, let me just get my calculator quickly. 180 minus 102 divided by 2, that's going to give me 39. And if this is 39, let's fill it on the page over there. So if this is 39, let's not use the highlighter there. If that is 39, remember that, and that is also 39, then how do I get C1? If the whole angle D and the whole angle C over here is 61, then I simply say 61 minus 39. 61 minus 39 will give me C1. ACO. Let's write it like that. Angle ACO will equal to 61 minus 39. And the reason for that is angles in same segment. Okay, with 61 minus 39, that gives me 22 degrees. All right, and that is the value of ACO. Right, this is an exam type question, 2019 DBE paper. We went through a proof. We went through a nice question over here as well. And I'm going to leave you guys with another question. which is question 11 from the 2018 paper. But before I do, let's just analyze the question so you can do it on your own. So I'm going to quickly go through Dr. Cape Town with you with regards to this question, and you can work through it on your own and come back and have a look. You can also access the memo on the DBE website. So let's go through it together. Dr. Cape Town, D represents your diameter. Does this question have a diameter? Let's read through the little write-up. In the diagram, O is the center of the larger circle. RTAP of the larger circle, RTAP. OP is the diameter. So yes, it does have a diameter, and it is the diameter of the smaller circle. So there's in fact two circles here. It's a small circle, and we've got a big circle over there. OP is the diameter of the smaller circle. And we also have the diameter over here, TOR, of the bigger circle, because O is the center of the larger circle. NP is a tangent to both circles at P, so this is a tangent to both circles. We also have perpendicular lines here. RN is perpendicular to NP, and then they give us that P1 is equal to X. So we said we have a diameter, we even have radii because we have a center O, that makes OR, OP, and OT radii. We have a cyclic quad as well. If I look at it, we have RPAT is a cyclic quad of the larger circle. We do not have parallel lines in this question, so we will not be able to use fun angles, but we do in fact have a tangent. It almost ticks all of them, a tangent NP to both the smaller circle and the bigger circle. All right, grade 11s, I'm going to leave you with that question. Work through it on your own. And I'm so glad to have you here for Euclidean geometry. Please make sure that you do go on the WhatsApp line and ask Maskey some questions on 072 091 0388. I hope to see you again next time. Thank you so much for joining.
And now we enter our next exciting chapter with the launch of Maskeyverse, an inspiring trio of innovations, our AI-powered learning companion, captivating TV content, and a vibrant playground for interactive learning, and our own dedicated app, all coming together beautifully to deliver learning outcomes through technology.